Okay, hello dear students. This my name is Tabish, and today I'm going to discuss an important topic of your subject, that is why an why electron does not reside inside the nucleus. Okay, and एक इलेक्ट्रॉन रिजाइड क्यों नहीं हो जाता है इनसाइड द न्यूक्लियस। हम न्यूक्लियस के बाहर इलेक्ट्रॉन को देखते हैं, ठीक है। फॉर एग्जांपल I will say that this is an atom and this is nucleus. Okay, it's a positive charge nucleus. Is having a positive charge. It's a very tiny mass objective with a high density. Okay, and this one is electron. So question is that if electron, proton plus neutron, that we call as a nucleon. Okay, if they are inside the nucleus, why we are not finding this particle inside the nucleus? So the question is, we're finding this in the circular orbits, what we call as stationary orbits. In a fixed energy, it's moving. Okay, for example, this one is two electrons. Yeah, this one electron. We're getting some electrons here, two, eight actually. Okay, so why we are finding the electrons outside the nucleus? Why not inside the nucleus? Okay, so this is the concept that I'm going to teach you. Okay, so we know how it happens. Okay, so let me rub this board. Okay, so actually what happens is that we know from the Heisenberg's uncertainty principle tells us that it is delta x and delta p is greater or equal to h cut by 2. Okay, so this is Heisenberg's uncertainty principle. You have read from your books that delta x is the uncertainty in position and delta p is that uncertainty in momentum, and it is greater or equal to h cut by 2. Now, what does this mean? What does Heisenberg's uncertainty means? It means that uh, we cannot find simultaneously the position and momentum of any particle. Actually, I am talking about at subatomic particles, very minute particles, which are very microscopic particles. For them, the Heisenberg's uncertainty principle is applicable. It's not applicable for large masses. Okay, make sure that for large masses it's not applicable. For large masses, I mean that classical system जो होता है उन पर ही applicable नहीं होता है. So it's not applicable for these particles. Yes, for small masses like electron, this is applicable. So it tells us that if we find the position of a particle, I want to find the position of the particle accurately, we will not simultaneously find the momentum with a greater accuracy. If one quantity is found with greater accuracy, then the other quantity will get more error in the measurement. So we'll get deviated from their accuracy. So if we get momentum with a greater accuracy, we'll deviate from position. This is what actually is Heisenberg's concept. I'm giving a little bit of touch. I hope that, but you remember this. Okay. Now we know that nuclear radius is of the order of 10 raised to power minus 15 meter. Okay, this is actually 1 4 millimeter. So if this much is the radius of the nucleus, this much is the radius of the nucleus, then that means we'll get an electron in this range. For example, if electron has to be inside the nucleus, though, so uncertainty that is possibly that we will find in this range. Because nuclear size is 10 raised to power minus 15 meters, so obvious is that if we had to find the electron, it will be in this range, right? It will be in this range, 10 raised to power minus 15 meters. So when we put up the values of delta x, we get delta p value. It is of the order of 10 raised to power. Something we'll get is, if we put the h cut by 2, it is actually it is h divided by, h cut is h divided by 2 pi, right? So for example, we get 6 point something. I'm just writing the order, 10 raised to power minus 34 and divided by delta x. It is of the order of 10 raised to power minus 15. And when you get it, it is 10 raised to power minus 34 and it is 10 raised to power 15. So it is 10 raised to power minus 30 minus 19, I think. Yes. Yes, it's of the order of 10 raised to power minus 19. That is uncertainty in momentum. I had dropped the values of other values. I just wrote order 10 raised to power minus 19. This much of the momentum uncertainty will be this. Okay. Let me raise this much what I have wrote down. It is a small board, and that's why I'm not able to write down for a longer period of time. Okay. Wait on. Down. Now, yes. So what we have got actually, this is uncertainty in momentum of the order of 10 raised to minus 19 and delta x with the uncertainty of 10 raised to minus 15. Okay. So it's momentum this much. Okay. So we know that relativistic energy is equal to it is p square c square. Actually, we are measuring the relativistic energy of this is relativistic energy. It is p square c square plus m naught square. It is c4. Okay. So this much is the relativistic energy of an electron. So we know that m naught square c4 is very less than p square c square. Okay, so what we can drop this one because this is in the square term, so it would be very small compared to this. So we're neglecting this, assuming that this is very zero, this much term, this term is zero, and this is p square c square, so it's an under root over 8, so it will get cancelled. What will get? It will be pc. Okay, so now putting the value E equal to momentum, what we have got of the order of 10 raised to power minus, it's 19. And 10 raised to power something we were getting, speed of light, 3 and 10 power 8. Is it? So when we will get calculation of, we'll get it 10 mega electron volt. So this much of amount of energy we'll get actually 10 mega electron volt. Let me again, is it? So wait a minute, wait a minute. Okay, so we're getting of energy equal to 10 mega electron volt. So this is the energy inside the nucleus. For example, if electron resides inside the nucleus, that it will reside inside the nucleus with this much amount of energy, 10 mega electron volt of energy. But as we know that beta decay, we are getting electron beta particle from the beta decay. Actually, we're getting electron from the beta decay. That's actually a neutron gets changed into proton with some particle of electron, some neutron. So when this electron is released in the beta decay. In the beta decay, actually, what happens is that one of the neutron gets changed into proton. It releases a proton with some amount of energy. Actually, this is a weak interaction. Beta decay is a weak interaction. Actually, what happens is that we have nucleons. So nucleons, protons plus neutrons. One of the neutron inside the nucleus gets converted into a proton. So in order to minimize the energy, because we know that nature allows to be in stable configuration. Okay, so in order to get the stability, it releases a proton and it release changes into a proton and release one electron. Okay, actually don't uh, give this interpretation that it is electron is inside the nucleus. No, actually neutron gets one of the neutron gets changed into proton and releasing an electron. Okay, it's actually neutron gets converted. Neutron is inside the nucleus, and neutron gets converted into proton, giving an electron. So this electron, the released during this transformation of neutron into proton, its energy is actually 3 to 4 mega electron volt. So this much of energy is with this much of energy is electron released inside the nucleus. So what we are getting 10 mega electron volt. So if nucleus if electron resides inside the nucleus, we are getting an electron with energy of 10 mega electron volts. Now nucleus neutron gets changed into proton, releasing an electron with 4 mega electron volt of energy. So there's a very much of difference. That's 6 mega electron. So 6 mega electron at volt is very much a more fundamental. We know that one atomic mass unit is equal to 931.5 mega electron volt. C square. So 6 mega electron volts is a very much of energy. So it's a very lot of difference. This so 10 mega electron volts, but we are getting an electron with only 4 mega electron volts. So that means inside the nucleus, it's greater energy inside the nucleus. So an electron with a 4 mega electron volt has to be outside the nucleus. So only proton and neutron were finding with this much of energy inside the nucleus. So that's why we are able to find electron outside the nucleus. So that's what actually our question was, that why an electron is not residing inside the nucleus. Okay. So I'll be giving you some other lectures. I hope that you understood this really well. So thank you so much for joining me. Thank you.